This little guy packs a big punch. It's the size of a walnut and can release the same energy as 2,000 liters of diesel. Not bad for a rock. With so much power comes great responsibility. For as fission reactions take place, the uranium fuel is slowly transforming into roughly 1/3 of the periodic table as solids and gases. These are the radioactive fission products that make nuclear waste dangerous, and they must be permanently contained. So beyond generating heat, the fuel needs to trap the fission products in place. In FCM fuel, millimeter-sized bits of uranium are trapped in tiny ceramic pressure vessels that can withstand extreme temperatures and radiation. These particles are then encased within a fully dense silicon carbide matrix, somewhat like encasing the fuel in a diamond. Silicon carbide is used for tank armor and has an extremely high melting temperature, far beyond the heat generated by the fuel. It is particularly resilient to radiation and does not chemically interact with other materials in the reactor. If the pellet is fractured, the fuel particles can remain intact as they are smaller than the smallest fragments. The core is assembled with enough fuel and graphite blocks to produce heat through self-sustaining fission reactions. This fully ceramic core has the lowest power density of any commercial reactor ever, allowing it to easily dissipate excess heat. To power it up, control rods are withdrawn and the fission reactions can begin. But these reactions slow down at higher temperatures. So to keep producing power, the reactor has to be cooled. If cooling stops, the reactor automatically shuts down. Helium carries heat out of the nuclear core. It is a harmless, noble gas, completely unreactive and stable. And while somewhat inefficient, it is the safest coolant available. Now, the problem with nuclear fuel is that it continues to generate heat even after the reactor is powered down. It will continue to generate roughly 10% of the original heat for hours and days to come. And if it's not cooled, that heat will pile up. The challenge with nuclear has always been to ensure the reactor does not damage itself when cooling is lost. The MMR can dissipate all excess heat passively and harmlessly into the environment in any scenario. Like a warm puck, it cools off just by sitting there. No moving parts or fluids, no operator actions, just simple cooling by conduction and glowing. This means the reactor can tolerate extreme conditions and survive undamaged. It can deal with complete withdrawal of all control rods. It doesn't need power to operate cooling pumps or emergency systems. The MMR doesn't even need coolant or natural airflow to stay at safe temperatures. It doesn't really need very much at all. Instead of designing elaborate safety systems against particular scenarios, we've designed a reactor that is inherently safe no matter the events. The MMR harnesses the fuel's formidable energy while fully containing its radioactivity during all encountered conditions, be it normal operations, worst-case failures, or permanent storage.